Hi guys, so welcome to our last part of lecture one. And in that part, we're gonna, discuss another interesting property of semiconductors, which is what are the current carriers in semiconductors? Okay, we know that electrons, do the job for metals or conductors, and they really contribute or make the current that that we all know till this moment. Okay, but thing is here a little different in semiconductors. And let's see how. Okay, so let's go back and draw this fancy covalent bond between silicon atoms and see what happens. So let's have a silicon atom here. So let's just write silicon instead. Silicon, 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 and do the covalent bond between them. So to here, to here, to here. Okay. And let's assume we are at room temperature. And, this is a snapshot of the same location at t equal to 0. So let's assume the time here is 0 second. And we take a snapshot of what's going on in the material at room temperature. At room temperature. Okay, we will find very interesting property here. So basically we said that since it's the room temperature, so maybe some electron will leave its bond and go to the conduction band. So let's assume this guy here leave its bond. Okay, so let's erase here this bond, make it just one electron, and right here that we have electrons that left this bond between these two atoms. Okay, good. Now, will it just be free forever? What's really happened is that, other electrons in other, bonds may move to fill this location. So let's, just take a copy and paste from the same figure we have here. And draw it again. Here, for example, okay. And let's say that here time, let's go back, time is equal to 1. For example, 1 second, 1 microsecond, something like this, okay, whatever. So we take snapshots. So at time equal to 1 second, for example, what happened is that, electron moves from this bond here and fill that missing bond here. Okay, so again, let's omit this here. Okay, and we say that another electron moves to fill this from that atom here, or that bond between these two atoms. Okay, then we continue. For example, at t equal to 3, we have the same structure again. Okay, and let's not to forget that this bond was free at t equal to 1, and this become filled, and maybe at t equal to t, time equal to t, time equal to 2 seconds, for example, electron moves from here and fill this gap here. Okay, so this become filled, another electron here, and this is the one. Okay, and this now become free. Okay, good. So when an electron moves from or leaves the bond and move to the conduction band, what happened is that this bond that he left will not become empty forever. No, some other electron in the same valence band will move from their bond to fill that gap or that hole, as scientists called it. So Basically, we have here holes. Let's hole here when this guy moves. Then we have another hole here when this guy moves from this guy, moves from this one to fill this one. Then we have another hole here when this guy moves from this to fill out this. Okay, so we have in the valence band another movement or electron motion to fill these gaps. Okay, so if we just see how this motion goes or the direction of this motion, it will be in that direction. Okay, this guy moves to here, then one here was moving to here, and so on. Okay, so this is electron motion in valence band. This is not the conduction band motion. This is another motion for the electron in the valence band. It's a lot easier, okay, to refer it in another way. That there was, we can imagine it in that way. We can imagine that this electron motion, it's electrons at the end, it's actually positive charges moving in the opposite direction. What are these positive charges? It's the holes. Yeah, the holes is that the broken bond that the electron moves behind, leaves behind when it moves to and go to the conduction band, can be imagined as, you know, positive charge and moving actually in opposite to these electrons. So these charge, let's draw it in green, are moving in that direction. And they call it holes, not H, but they call it B. And they refer to its charge as positive because they are moving, you know, in opposite direction of the electron. But remember, this is just, you know, a kind of modeling. But what really happened is that the electrons were moving in the valence band from a hole to a hole to a hole, you know. Okay, so we can imagine that it's actually the holes that are moving, not the electron. And we can give it even, we can model it as also positive charge. And this turns out to be a lot easier to deal with it rather than dealing with what actually or what really happened, which is electron motion. Okay, so let's imagine it more. So let's draw the energy band diagram. Here is the energy band diagram. Here is the energy gap. Okay, and here is the valence, the electron shells. And when electron moves from here to here, okay, this electron will make current, will contribute to the current conduction in the conduction band, but it will leave behind the hole when it moves. Let's draw it in green, a hole like this. Okay, and when electrons moves in the valence band from a bond to fill this hole, it will leave behind another hole. So we can move, we can here imagine that there is a whole motion or a positive motion opposite to the direction of the electrons in the valence band. Okay, good. Now, based on that, we can say now that we have two kinds of current carriers in semiconductors. The first one, which we all know, is electrons in the conduction band. And the other one now that we have discovered is the are actually the holes, and both contribute to the current, the total current. I mean, if you have a piece of silicon, okay, and you connect a battery terminals to it at room temperature, you will find there is a current. This current not only comes from the electron motion in the conduction band, but also the whole motion in the valence band. The electron motion are the motion of negative charge, the whole motion or the motion of positive charge. Okay, and now let's ask ourselves a question, which are if we catch a piece of silicon in nature, okay, and we try to measure the density of the electrons and the density of the holes, which will be greater than the other, or the holes are greater than the electrons, or the electrons are greater than the hole. Okay, I will give you 5 seconds to think about it. Okay, 1, 2, 3, 4, 5. If your answer were that electrons are greater or holes are greater, this is incorrect. This is wrong. Basically, because the nature of in nature we usually find materials neutral in charge. The net charge usually 0. Okay, and this is actually the common sense, because if we go back to the theory of behind this creation of holes, how a hole created in the first place? Basically because an electron leaves its bond and go to the conduction band, so it leaves behind a hole, right? So for each electron generated in the conduction band, a hole generated in the valence band. So let's write this. So for each electron generated in the conduction band, a hole generated in the valence band. Okay, so if we call the density, remember the density from last lecture, how many carriers you have per centimeter cube or meter cube or millimeter cube or micrometer cube or whatever cubed. Okay, remember this density. So if we call the density of electron n and the density of holes b, then basically they are equal. If you have 100,000 electron per centimeter squared, you must have 1,000 hole per centimeter squared. Sorry, cube, not squared, cube. I keep making this error. It's a cube, not a square. So if you have again 1,000, so if you have 1,000 electron per centimeter cubed, you will have 1,000 hole per centimeter cubed. Okay, so all the time n equal to b. And what is n in the first place? As we said last time, it is 5.2 10 to the power 15 t to the 3/2 exponential minus eg over 2kt. So n equal to b equal to such term. Okay, both of them increase by increasing the temperature or decrease by decreasing the temperature. Both of them increase by decreasing the energy gap, or decrease by increasing the energy gap. Okay, let's now ask ourselves very important questions and see, which are basically, an opening question for the next, lecture. So the first question that we have here, how many, for silicon at room temperature, how many hole or electron per centimeter cube? So if you we know Eg. If we look at the equation here, we know Eg for silicon. So 1.12 electron volt. We know K. It's Boltzmann constant. It's known. Okay. T at room temperature 300 degree Kelvin. So we can determine it, okay? So for silicon, at room temperature, N equal to B equal to 10 to the power 10 charge or carrier charge per centimeter cube. Okay, this is at T equal to 300 degree Kelvin. Okay, now the great question is this, it's of course, it's a very big number. This is 10 billion charge per centimeter cubed. So based on that number, is silicon is a good conductor or a poor conductor? So the question here is silicon is or considered a good or a bad conductor? You have 5 seconds again. 1, 2, 3, 4, 5. It's a poor one. Okay. Why is that? To know poor or good, we should, compare it to the best conductors we know so far, metals, right? Something like copper. So in our electric circuit, we usually use copper or aluminum for wiring. Okay. So let's compare it to copper. So for copper, so the answer here, it is poor. Let's compare it for copper. For copper, N equal to 5 times 10 to the power 22. Okay, that's a huge number. Okay, that's a huge number. So if we relate them together, 10 to the 10 to the 5 to the 10, 22, if we divide by 10 to the 20, 10 to the 10, it will be 1, 2, 5 to the 12 in copper. That means for each carrier in the silicon that contribute to the current in centimeter cube, there are 5 trillion. This is a trillion, which is 1,000 billion. 5 trillion, electron or carrier that contribute to the current in copper. That's why it's really a poor conductor. It's conductor, but it's very poor compared to copper. Okay, and we have a similar situation with aluminum as well. Okay, now the big question is how to increase the conductivity or in the carrier density. If we increase the carrier density, we should increase somehow the conductivity of semiconductors, silicon specific. Okay, one special, one obvious answer here is that just look at the equation here. Okay, look at the equation. We can increase temperature, and by the way, it's a strong function with temperature. T to the power 1.5. If it's just a T, it's a linear relation, but it's 1.5, so it's stronger. I mean a higher proportionality than just direct proportionality, which is in linear relation. Okay, but it turns out we need to increase the conductivity or the carrier density to acceptable level. We need a really very high temperature. Okay, very high, and we're gonna see examples for this next time. Okay, but it turns out there are more smarter way to increase the conductivity of silicon, and that's the topic of the next lecture 2, which is doping. Okay, by adding other atoms, what we call dopant atoms, to the silicon crystal structure. So the crystal, something like this is called the crystal. of silicon. That will increase, the conductivity of silicon. So stay tuned, guys, for the next lecture, lecture 2, in which we will start by this interesting topic of doping. See you. Bye bye.